Welcome back, fellow space cadets. I'm Jason. Today, I'd like you to prepare to have your mind absolutely blown and your cosmic curiosity piqued as we embark on a journey to unravel the enigma of dark matter. That's the invisible form of matter that forms most of the stuff in our universe, yet we can't even see it. Honestly, it is one of the most important and incredible discoveries of the last 100 years. So grab your telescopes and strap in because things are about to get pretty weird. Now, to grasp the concept of dark matter, the first thing we have to do is to address the most obvious question. What exactly is dark matter and why can't we actually see it? Well, my friends, imagine this. You're gazing up at the night sky, you're captivated by all of the twinkling stars, yet unbeknownst to you, there's a hidden form of matter, what we now call dark matter, that remains elusive to our senses, something you can't directly see, but that you know is there. Now, according to current theories, dark matter constitutes a staggering 85% of the universe's mass, yet it interacts with neither light nor other forms of electromagnetic radiation. It's almost like the universe harbors a silent, invisible companion that influences cosmic structures without being seen at all. Now, I'd like to stop for a second and talk about this. Think about what we're saying. We look out into the cosmos. Everybody would agree all of the stars in the night sky are just amazing and mesmerizing to look at. When you go out into the country in a dark place, you can see the band of stars across the night sky that we call the Milky Way, right? But all of those stars are in our own galaxy. They're local to us, right? You know, to see stars that are in other galaxies, those are much, much, much farther away, and you just see like little fuzzy blobs of galaxies in telescopes that we know contain billions and billions of additional stars. And there's additionally billions and billions and billions of additional galaxies out there. So anyone would agree that looking up at that just hits you over the head with an amazing sense of grandeur. What we're saying is that amount of stuff that you see in the sky, right, that is a tiny bit, maybe 10 to 15% of what actually exists in the universe, right? The rest of it, about 85 to 90%, is what we call dark matter. And it's there, and it has gravitational influence, but it doesn't interact with photons at all. So you don't see it, and it's very, very hard to detect. So, and not only is it a tiny part of our universe, it is the vast majority of everything that's out there. That is absolutely incredible. Now, I'm going to say right now, for the rest of what we're going to talk about, we don't have all of the answers. We're at the very beginning of this journey, right? But the first thing we want to really talk about is, what could dark matter actually be composed of to behave this way? While there are many theories out there proposed by many different scientists, right, one prevailing hypothesis suggests that dark matter actually consists of what we call exotic particles that interact solely through gravity. These particles, which are unlike ordinary matter that you have experience with, do not emit or absorb or reflect any light at all, rendering them very, very difficult to detect from the Earth. Now, I don't want this to blow by you too fast. What we're basically saying is that ordinary matter that you have experience with has gravity. We know that. But it also interacts with photons. And our eyes are photon detectors. So when a photon of light or light hits matter, it interacts with the matter, it can bounce off. The bouncing off of a mirror is an interaction with matter. Photons and matter interact with each other. They can emit photons, they can absorb photons, reflect photons. Any interaction that you think about in everyday life that involves light also involves matter. But what we're saying here is that there appears to be most of the universe consists of something else that only interacts through gravity, right? So we know that dark matter has some sort of gravitational influence, but it does not interact with photons. And that makes it really, really hard for us to detect. What I'd like to talk about for a second is how we see things in general. right? When you look at a light bulb, what's happening? Like an incandescent light bulb. Electricity flows to the light bulb, and the electricity causes friction inside of the filament of the light bulb, and the light bulb begins to glow. The reason it's glowing is because the atoms of the tungsten in the filament have electrons in their outer electron cloud. And those electrons, when the electricity goes through it and the friction happens, they begin to be excited to a higher energy orbital. That means farther away. They absorb energy and they go farther away. And then as the electrons decay back down into the lower orbit, the lower energy level, they emit a photon, right? So the interaction of electrons going up and down and jiggling in their orbits either absorbs photons or emits photons. That's what I mean when I say matter interacts with photons in light, right? Because light is a photon of energy, right? So that's what we mean, is that all interactions that you have from light bulbs, it comes from matter. The electron clouds jiggling, photons coming out. Let's think about a mirror. Photon goes in, interacts with the material, usually a coating of silver, and then a re-radiation of photons come out of those atoms, okay? Anything you see where photons are hitting it, and then you see a reflection of some sort, so pretty much anything that you see in everyday life comes from an interaction between the light and photons, right? Things inside of the sun, all of the light from the sun comes from nuclear fusion. Obviously, that light comes from atoms fusing together. Atomic bomb exploding, fission exploding, it comes from matter. I challenge you to come up with an example of light that you can see in everyday life that does not come from matter or does not interact with matter. I don't believe you're going to be able to do it. So we don't think about it that way, but photons of light and atoms of matter, they kind of go together like peanut butter and jelly, and they interact constantly. What we're saying is that there is gravitational interactions, which we'll talk about in just a second, that show that there has to be more stuff in the universe than we can see, but it doesn't interact with any photons. No photons come out, no photons get reflected, and no photons really just do anything with it at all. They just pass right through, so we have no way of seeing them. And to drive home the point even a little bit further, even air, right? This clear gas that we have called air interacts with photons. When you think about a hot barbecue pit or something like this, and you can see the shimmering, the hot gases coming right off, right? The light passes through that hot shearing of air there, and you can see the light taking different paths. That's the wavy kind of like distortion that you see when you look over a very hot, clear layer of air, or a mirage is a similar sort of thing. And obviously reflection and refraction through water and air can happen as well. And so the bending of the colors of the rainbow, you have the light coming in, it spreads into the spectrum. That's an interaction between light and matter. Even clear things like air are interacting with photons. So I'll leave you with one question that nobody knows the answer to, but if there exists all this dark matter out there and it doesn't send any light anywhere, and we know that it exists as more than 80% of the mass of the universe, then is it possible that out there somewhere is a dark star? A whole star clumped together of this dark matter that's just out there somewhere, that we can't see it. We don't see the stars that don't emit any light. So is it possible that all the stars that we see in the night sky is completely dwarfed by dark matter stars everywhere? We just can't see them. Is it possible? It is possible. Nobody knows the answer. Now, with such an exotic form of matter, there has to be strong evidence, right? And there is strong evidence. Despite its elusive nature, dark matter leaves its subtle traces of its existence, but we don't see it. It leaves other evidence behind. Now, by observing the gravitational effects that dark matter exerts on galaxies and the bending of light as it goes through the cosmos, scientists and astronomers have amassed compelling evidence supporting the presence of dark matter. Now, probably right now, hopefully you're saying, well, wait a minute. You just told me that dark matter doesn't interact with light, but now you're saying that it can kind of influence light and the path of light, but you just said it doesn't interact with light. Well, it indirectly interacts with light. And what I mean by that is we now know that gravity in general is not just a force that mysteriously happens over a distance. Gravity comes about because a massive object, pretend that this is a sun, for instance, a massive object like a sun distorts the space-time that it's in the vicinity of that star. And anything moving through the universe, even photons of light that don't have any mass, they're always trying to follow the shortest path through space-time. And so if there's no star there, it's just going to appear to go in a straight line. And so that's what we always kind of see, things moving in a straight line. You know, an object in motion tends to stay in motion. However, if you put a star in the way and you're looking right on the edge of that star, and you're looking at the stars in the distant background, like if we're looking at the sun right here, and we're looking at distant stars in the background right on the edge of the sun, like during a solar eclipse, and by the way, this has been done before, then what we will see is the stars in the background will be in a very slightly different position than where they should be, because the starlight coming here is bent by the sun. The path of it is bent by the sun, and so we see those stars in a different position than if the sun weren't there. This experiment was done in the early 1900s during solar eclipses, because when the sun is covered up by the moon, the sky gets dark and we can see some of the stars behind the sun, or not directly behind, but the ones that are near the edge of the sun. And what we can see is very slight differences in their position from where they should be. So what that means is as the starlight travels very near a star, it gets bent very slightly. Now, photons don't have any mass. So we always think of gravity affecting mass, but actually gravity affects anything moving through the universe, even photons of light that don't have any mass. They get bent because the curvature of space and time changes near the surface of a star, or near the boundary of a star there. So why am I mentioning that? Even though dark matter does not directly emit photons, like a star emits photons, it emits light, right? Even though dark matter doesn't emit photons directly or reflect photons directly, if you had some kind of mass of dark matter, and you had some stars behind it, if the photons of light were passing near some clump of dark matter, the dark matter is warping space-time and can change the path of the starlight as it goes nearby, just like a star can. So even though it doesn't directly emit light, we can't directly see them, we see indirect effects. Other stars in the background that are in slightly different positions, and other evidence that I'll give you in just a second indicating the presence of dark matter. So people are looking for that out there to confirm these theories. So what I want you to do is I want you to start to think of dark matter as sort of like a silent architect of the universe. It sculpts the cosmic landscapes and it can influence it, but only indirectly. And so it sort of guides the motion of celestial bodies through gravity, but through no other interaction. It's kind of like an invisible hand orchestrates the dance of galaxies, shaping the fabric of space and time, but something that we can't directly see or interact with. Now, let's take a minute to dive a little bit deeper into the scientific evidence supporting the existence of dark matter. I want you to picture yourself aboard a spacecraft. You're venturing out into the vast expanse of space. And as you look through the window, you take in the breathtaking spectacle of all the distant galaxies suspended in the tapestry in the inky blackness that's out there. Now, beneath the surface of this cosmic picture that you see in front of you, there's a puzzle that scientists have been looking at for decades that observes stars on a daily basis. And it's called the rotation curve of galaxies. I want to say that again. It's the main evidence for dark matter. It's called the rotation curve of galaxies. Now, in a universe governed by the laws of gravity that we more or less understand pretty well, galaxies should exhibit a predictable pattern of motion. In other words, galaxies rotate much like solar systems, and we have math that should predict exactly how they rotate because we understand more or less gravity. Now, let me stop for just a second. We do not understand the origin of gravity. There are theories in quantum gravity and trying to make gravity a quantum effect. Like, we don't have all those details worked out. But what I'm trying to say is on large scales, we have equations that govern the motion of objects in a gravitational field, and those are very, very accurate. We can calculate where the planets will be at a given time in the future based on our theories of gravity. We have Newtonian gravity, the classical theory of gravity, which is fairly accurate, but not super accurate for large, very, very accurate calculations. But we also have Einstein's theory of gravity, which relies on space-time curvature being the cause of gravitational force, so to speak. And that's a much more complicated mathematical theory, but it's very, very accurate. We have equations to predict how things will move. That's why we can send space probes to planets way out in space and get there. And by the way, when we shoot a spacecraft into space, we're aiming the spacecraft at a place in space where the planet is not yet at. So you're not aiming for the planet, you're aiming for where the planet will be 15 years in the future. So we can do that very, very well. And because of that, we know the mass of the galaxies. And so we should be able to calculate how the galaxy should be rotating, how fast, exactly the velocity of all the stars going around the galactic center and things like that. So if we're in a universe where the law of gravity exists the same all over the place, even across the universe, galaxies should exhibit a predictable pattern of motion with their stars orbiting at velocities that are determined by their distance from the center of the galaxy. However, when scientists actually observe this, it's really perplexing because there's a discrepancy. Stars at the outskirts of the galaxies orbit at an unexpectedly high velocity, and this defies the laws of physics. Now, this phenomena is known as the galactic rotation curve, and it suggests the presence of an unseen mass that we now call dark matter that exerts a gravitational pull on the visible matter. Now, to recap this, we have a fairly good descriptive theory of gravity. We don't know exactly where it comes from, but we know how to calculate how things will move, and we have practice with doing that in our solar system. And we look at stars in our immediate vicinity, and we can calculate how they move as well. But when we look at galaxies from far away, and we monitor how the stars are rotating, there's a discrepancy between our calculations for how they should move, how they should rotate, how fast they should rotate, and how fast they're actually rotating. And the speed of something orbiting the center of a galaxy should be related to how far away it is from the center, but it appears that basically there's a discrepancy in such a way that there has to be some sort of unseen mass, and not just a little bit of unseen mass. This is not a tiny, a tiny discrepancy. This is a very large discrepancy. Now, we're going to get into all the theories of exactly what dark matter is in just a second, but let me just say up front, it's possible that our theory of gravity is just not correct on large scales. That was one of the early suggestions for dark matter. Instead of another form of matter, maybe our theory of gravity just doesn't work on galactic scales. In other words, our calculations for gravity might work fine inside of the solar system and maybe even several light years away, but when you have very, very, very large distances, it's possible that our equations that govern the gravitational forces are just not right on very, very large scales. And people are still pursuing that, and they're trying to modify, Einstein's theory of gravity and such to account for this. But there have been a lot of technical difficulties getting that to work. There isn't an easy way to modify these theories to make them match all of the data, so the prevailing theory isn't really that we don't understand gravity, but the prevailing theory is actually this new form of matter that just doesn't emit photons and doesn't interact with photons that we call dark matter. I'm going to take a second to try to describe this for you in a simple to understand way. So basically, I want you to imagine a thought experiment where here is the planet Earth. And on this Earth is a mountain. Here we're going to talk about orbits, and so you can understand the discrepancy that leads to dark matter. I exaggerate the height of this mountain, obviously. Now you stand at the top of this mountain, and you throw a rock horizontally, straight parallel to the ground, but you only throw it relatively, not so hard. And so what happens is the rock comes down here and hits the surface of the Earth, maybe 1,000 kilometers away or 200 kilometers away, something like this. But then you get a much stronger person to throw it again horizontally. And what happens is it goes a little bit farther, but eventually it does hit the surface of the Earth much, much farther away. But then you stand up there and you get the strongest person in the world to throw it, and again horizontally, and what happens is it just gets a little bit farther away, but eventually the gravity of the Earth just pulls it down. You see what's happening? You're approaching closer and closer to an orbit. What we do when we send a ship into orbit is that we put a rocket on there that gives it enough horizontal velocity that what happens is it's always falling towards the ground, but it just never quite gets there, and it comes back to its starting point. And so a rocket sending a ship into orbit is not about getting high. I mean, you have to get high because you have to get out of the air. You see, in order to keep going around and around and around, you got to be out of the air because the air slows you down. But what you really need to do is you need to be going sideways. And you need to be going sideways very, very fast so that you kind of go fast sideways so much that even though gravity is pulling you down, it's actually, you're going so fast horizontally that it's pulling you down at the same rate as the curvature of the Earth. And so that you end up back to your starting point, and because you're out of the atmosphere, you can keep doing this over and over again until eventually you want to come home. And you come home by actually slowing yourself down and braking so that you then fall into the atmosphere and land your spaceship. That's what an orbit is. Now we have very accurate equations to govern orbits of planets and spacecraft, and we do that all the time. So we know how it works very, very, very accurately. This is not an inexact thing. All right. Now what we've learned from the equations that govern orbits like this is that the the speed required to orbit in a spaceship, it depends on how far away you are from the planet. It depends on the planet too. It depends on the mass of the planet, right? It depends on lots of things. But in general, it depends on how far away you are. So if you're very close to the planet, you have to be moving really, really fast in order to orbit around it. Because think about it, if I was orbiting this high off the ground, I would have to be going super fast to get away from the ground before I hit the ground. The farther I am from the planet's surface, and I'm way out here, then I have to orbit, I have to be moving horizontally much slower in order to make it, to not hit the ground, I guess is what I'm trying to say. And the math behind that doesn't matter the details, but I just want you to know that the distance you are from the planet governs how fast you need to be in your orbit to stay in orbit. And so the same thing with a galaxy. A galaxy, there's the galactic bulge in the center, and there's all the stars in the pancake around the galaxy, right? And so we know from our theories of gravity that the stars near the galactic center should be moving at a different speed than the stars far away. Just like I'm telling you that orbiting close to a planet and far from a planet requires different orbital speeds. So if we see the galactic bulge and we can estimate how much mass is there, we know how much is mass in the center of the galaxy, then we know how fast all of the stars should be orbiting all the way around the edge of the galaxies. But when we finally got scientific equipment sensitive enough to really determine the rotation curve, is what it's called, of the galaxies, we figured out that they're going the wrong speed, and not by a little bit, by a lot. And there has to be either our theory of gravity wrong, and that's possible, but unlikely, or there's some other mass there that we can't see because we can see everything else. There has to be some other force of gravity by some other exotic particle pulling on everything that does not emit light. And that's the main evidence for dark matter. And we don't just see it with one galaxy here and there, we see it everywhere, right? So there has to be something big going on. That's why we think 85% of everything we see or everything in the universe is actually completely invisible, called dark matter. Specifically, what the evidence actually shows is that these stars at the edge of the galaxies are actually moving way too fast compared to what we predict. And that's the main evidence for the existence of some other exotic matter that exists almost everywhere in the universe. Now, in addition to the galactic rotation curves, gravitational lensing provides further evidence for the existence of dark matter, independent evidence. So I want you to imagine light, as we were talking about just a minute ago, from a distant galaxy traversing all the way across the universe, only to encounter a massive object in the way, a galactic cluster, something like this, that bends the light and distorts the path of the photons. So this is gravitational distortion, what we talked about just a minute ago. It's kind of akin to a cosmic funhouse mirror that distorts things and offers astronomers a glimpse into the hidden realm of dark matter. Now, by studying the bending of light, scientists can map the distribution of dark matter in the universe, revealing its pervasive influence on cosmic structure. And this kind of research is ongoing all the time as we speak. So now that we've explored the concept of dark matter and its mysterious halo, let's dive into the fascinating world of the competing theories that are out there about dark matter and what it might actually be. The scientific community is buzzing with lots of activity and lots of different hypotheses, each attempting to unravel the nature of this invisible form of matter that's out there. So let's take a tour through the cosmic debate and see what theories are currently on the table and which ones are currently leading the pack. So first up, we have the WIMP hypothesis, and yes, that's not a typo, that's actually called the WIMP hypothesis. We're not talking about a cowardly ghost here. WIMP actually stands for weakly interactive massive particle, or weakly interacting massive particles. These are theoretical particles that are heavy and only interact via the weak nuclear force and gravity, and that makes them notoriously difficult to actually detect, again, because it doesn't interact with photons. So you can kind of think of WIMPs as the strong, silent type of the particle world, lurking in the shadows and influencing the universe from behind the scenes. And let's not forget another competing idea called the machos. That's the massive, astrophysical, compact halo objects. Now, this theory suggests that dark matter might be made of ordinary matter that we just haven't seen, like black holes, neutron stars, brown dwarfs, things like that. However, machos have fallen out of favor because surveys of our own galaxy and of other galaxies haven't found enough of these objects to account for all of the dark matter. I mean, in the beginning, people thought that maybe galaxies were just completely surrounded by black holes everywhere. Black holes don't emit any light because they suck all the light in, nothing gets out. So maybe there's just like way more black holes out there that have a gravitational influence that we just can't see. But actual surveys of that just don't quite add up with what we should actually see. So the prevailing theory is not the macho, but it's actually the WIMP, which is the weakly interactive massive particle, which means particles that interact with gravity and other forces, subatomic forces, but not through photon interactions. Now, with all these theories swirling around, which one is currently the leading contender based on data and observation? Now, the most favored theory among astrophysicists, as we talked about just a minute ago, is the WIMP hypothesis. I want to talk a little bit more about why. The evidence from the gravitational lensing, the cosmic microwave background, and the behavior of galaxies all point towards dark matter being made of these particles that really only interact through gravity and the weak nuclear force. So for instance, observation of the cosmic background, the cosmic microwave background, the afterglow of the Big Bang shows patterns that are best explained by the presence of dark matter in the form of these WIMP particles that really don't interact with photons. Right? Additionally, the way the galaxies rotate and the distribution of the galaxy clusters suggests that there's a significant amount of unseen mass influencing their dynamics, which is all characteristic and consistent with the WIMP hypothesis. Moreover, experiments like those conducted by the Large Hadron Collider and various underground detectors are actively searching for WIMPs to actually trying to detect them. Now, although we haven't directly detected them yet, the indirect evidence continues to mount, making these WIMPs the front runner in the race to identify dark matter. Now, just after the Big Bang, dark matter gravitationally influenced the regular matter which was already forming and leaves kind of a fingerprint on the cosmic background radiation. At least that's one theory. And so we're looking for this fingerprint in the cosmic microwave background radiation right now. So even though dark matter doesn't like emit photons and is directly visible, we think that in the early phases of the universe, when matter was forming and lots of dark matter was around, they gravitationally interacted with each other. Now we're searching for evidence of dark matter in the cosmic microwave background radiation. And the way that would work is because if you take yourself back to the Big Bang before any of this other galaxies and stuff formed, just atoms were forming, regular matter, and dark matter supposedly, or we suppose at that time, was also present. Now they don't directly interact, but gravitationally they can influence each other. So even though dark matter isn't like directly interacting with matter, gravitationally it can influence the distribution of matter in the early universe. And since the cosmic microwave background comes from the expansion of the universe and gravitationally is affected by the distribution of galaxies, we think that, 13 billion years later, if we look at the cosmic microwave background, we might be able to see some fingerprints on that cosmic microwave background radiation that we see in the sky today that would extend from its influence all the way back to the beginning of the universe when dark matter was influencing regular matter when everything was forming to begin with. So we're looking for evidence of dark matter also in the cosmic microwave background. As we unravel the mysteries of dark matter, we're confronted with profound questions about the nature of the universe and our place within it. Everything suddenly seems more complicated and we seem, in my opinion, a little bit smaller, right? So from the depths of the intergalactic space to the inner workings of subatomic particles, the quest to understand dark matter unveils the wondrous complexity of the cosmos. I mean, when I look out there, I just honestly feel a little bit smaller, humbled, but also grateful at the same time. In conclusion, fellow humans, the enigma of dark matter stands as a testament to the limitless wonders of the universe. From its invisible presence to the subtle clues it leaves behind, dark matter challenges our understanding of the cosmos, and it also inspires us to explore the unknown. I'd really like to thank you for hanging out with me, for pondering these things, for exploring this with me. I really hope you learned something. I really hope you enjoyed this topic. Please do send me an email, drop me a line, let me know what you think, and always remember to stay curious. Learn anything at mathandscience.com.